Introduction to Reliability-Centered Maintenance, RCM. Reliability-Centered Maintenance, RCM, is a structured and systematic process used to determine the most effective maintenance strategy for ensuring the reliability and safety of physical assets. Originally developed in the aviation industry, RCM has since been widely adopted across various sectors, including manufacturing, energy, transportation, and utilities. RCM focuses on understanding how and why equipment fails and prioritizes maintenance tasks that prevent or mitigate those failures. It shifts the mindset from traditional time-based maintenance to a more proactive, condition- and risk-based approach. The primary purpose of RCM is to ensure that systems continue to perform their intended functions in their operating context with the desired levels of reliability, safety, and... Let's start with more details. Reliability-Centered Maintenance, RCM. Any RCM process shall ensure that all of the following 7 questions are answered satisfactorily and are answered in the sequence shown as follows. What are the functions and associated desired standards of performance of the asset in its present operating context functions? Example: pump producing certain pressure and flow. In what ways can it fail to fulfill its functions? Functional failures. What is counted as failure? What causes each functional failure? Failure modes. Say what could be reason for low pressure or flow. What happens when each failure occurs? Failure effects. Or how it will be observed. In what way does each failure matter? Failure consequences. To determine the magnitude of the likely risk. What should be done to predict or prevent each failure? Proactive tasks and task intervals. To work out preventive and predictive tasks at failure mode level. What should be done if a suitable proactive task cannot be found? Default actions. Before we start with actual RCM process, it is vital to set the levels of analysis and other prerequisites are to be set in. Select the level of analysis to be carried out. The level of detail which is ultimately selected should enable a suitable failure management policy to be identified. Higher levels, less detail, should be selected if the component or subsystem is likely to be allowed to run to failure or subject to failure finding. Lower levels, more detail, need to be selected if the failure mode is likely to be subjected to some sort of proactive maintenance. It's important to have a function's complete definitions. Primary functions, which summarize why the asset was acquired in the first place. This category of functions covers issues such as speed, output, carrying or storage capacity, product quality, and customer service. Secondary functions, which recognize that every asset is expected to do more than simply fulfill its primary functions. Users also have expectations in areas such as safety, control, containment, comfort, structural integrity, economy, protection, efficiency of operation, compliance with environmental regulations, and even the appearance of the asset. Let's look any details about each RAM question and their context. What is functional failure? Total inability to function. Partial failures, where the asset still functions but at an unacceptable level of performance. Clearly, these can only be identified after the functions and performance standards of the asset have been defined. What is failure modes? All the events which are reasonably likely to cause each failed state. These events are known as failure modes. Reasonably likely failure modes include those which have occurred on the same or similar equipment operating in the same context. Failures which are currently being prevented by existing maintenance, and failures which have not happened yet, but which are considered to be real possibilities. What is failure effects? It describes what happens when each failure mode occurs. It includes all the information needed to support the evaluation of the consequences of the failure. It is these consequences which most strongly influence the extent to which we try to prevent each failure. If a failure has serious consequences, we are likely to go to great lengths to try to avoid it. A great strength of RCM is that it recognizes that the consequences of are far more important than their technical characteristics. In fact, it recognizes that the only reason for doing any kind of proactive maintenance is not to avoid failures per se, but to avoid or at least to reduce the consequences of failure. Next, the central concept of RCM, how consequences and their impacts are determined and guide the RCM process. The RCM process classifies these consequences into 4 groups as follows. Hidden failure consequences. Hidden failures have no direct impact, but they expose the organization to multiple failures with serious, often catastrophic, consequences. Most of these failures are associated with protective devices which are not fail-safe. Safety and environmental consequences. A failure has safety consequences if it could hurt or kill someone. It has environmental consequences if it could lead to a breach of any corporate, regional, national, or international environmental standard. Operational consequences. A failure has operational consequences if it affects production, output, product quality, customer service of operating costs in addition to the direct cost of repair. Non-operational consequences. Evident failures which fall into this category affect neither safety nor production. Proactive tasks. Proactive task in RCM is simply all preventive task done to avoid failures. Proactive tasks are tasks undertaken before a failure occurs in order to prevent the item from getting into a failed state one. They embrace what is traditionally known as predictive and preventive maintenance. RCM divides proactive tasks into three categories: scheduled restoration tasks, scheduled discard tasks, scheduled on-condition tasks. Scheduled restoration entails remanufacturing a component or overhauling an assembly at or before a specified age limit, regardless of its condition at the time. Scheduled discard entails discarding an item at or before a specified life limit, regardless of its condition at the time. On-condition task. Some functional attribute is monitored continuously and an alarm is raised when monitored attribute values crosses set value. The majority of these techniques rely on the fact that most failures give some warning of the fact that they are about to occur. These warnings are known as potential failures. Potential failures defined as identifiable physical conditions which indicate that a functional failure is about to occur or is in the process of occurring. And if none of proactive tasks available, we need to select some default tasks. Default actions. RCM recognizes three major categories of default actions as follows. Failure finding. Failure finding tasks entail checking hidden functions periodically to determine whether they have failed, whereas condition-based tasks entail checking if something is failing. Redesign. Redesign entails making any one-off change to the built-in capability of a system. This includes modifications to the hardware and also covers once-off changes to procedures. No scheduled maintenance. This default entails making no effort to anticipate or prevent failure modes to which it is applied, and so those failures are simply allowed to occur and then repaired. This default is also called run to failure. Once the consequences are determined and proactive tasks understood, the next is to assign the suitable maintenance policy for consequences. Maintenance task selection. For hidden failures, the failures which are not evident by their own, a proactive task is worth doing if it reduces the risk of the multiple failure associated with that function to an acceptably failure low level. If such a task cannot be found, then a scheduled failure finding task must be performed. If a suitable failure finding task cannot be found, then the secondary default decision is that the item may have to be redesigned, depending on the consequences of the multiple failure. For failures with safety or environmental consequences, a proactive task is only worth doing if it reduces the risk of that failure on its own to a very low level indeed, if it does not eliminate it altogether. If a task cannot be found which reduces the risk of the failure to an acceptably low, the item must be redesigned or the process must be changed. Failure with operational consequences. A proactive task is only worth doing if the total cost of doing it over a period of time is less than the cost of the operational consequences and the cost of repair over the same period. In other words, the task must be justified economic, no scheduled grounds. If it is not justified, the initial default decision is maintenance. If this occurs and the operational consequences are still unacceptable, then the secondary default decision is again redesign. Failure with non-operational consequences. A proactive task is only worth doing if the cost of the task over a period of time is less than the cost of repair over the same period. So these tasks must also be justified on economic grounds. If it is not justified, the initial default decision, no scheduled maintenance, is again, and if the repair costs are too high, the secondary default decision is once again redesign. This approach means that proactive tasks are only specified for failures which really need them, which in turn leads to substantial reductions in routine workloads. Compare this with the traditional approach to the development of maintenance policies. Traditionally, the maintenance requirements of each asset are assessed in terms of its real or assumed technical characteristics without considering the consequences of failure. The resulting schedules are used for all similar assets, again, without considering that different consequences apply in different operating contexts. This results in large numbers of schedules which are wasted, not because they are wrong in the technical sense, but because they achieve nothing. The table objectively showing the task selection. Pause the video and observe the table in the light of knowledge grasp in the earlier part of the video.